In our final topic of this lesson, we want to talk about statically indeterminate torque systems. So in a statically indeterminate system, we have something like this circular rod, and we would fix it at both ends. All right, and now we're going to come in somewhere along the length, and I want to apply a torque. So I want to come in here and apply a torque. So I think you'll have to do some imagining with me because I don't have 3 hands here. So if I rotate it here, I can't do it. But if we can imagine that looks something like this as it rotates, what do we think has to happen at the supports? Hopefully you see that because I'm twisting here at C and it's counterclockwise as applied to the rod. Again, if I sketch my x-axis in here, then at the supports, I need to have something counteracting that. So at support A, I'll probably have a torque at A that's clockwise, and at B, I would likewise have a torque that's clockwise. Now, just like when we talked about statically indeterminate systems with axial force, this one's statically indeterminate because we don't know how much torque is being handled by B, and we don't know how much is being handled by A. But we know that together, A and B have to resist the torque applied at C. And so that speaks to our first tool in our engineering toolbox of equilibrium. So if we said from equilibrium, we sum our moments about the x-axis, I can state that TC minus TA minus TB has to equal 0. Or I get the formula that TA plus TB has to equal TC. All right, so this is equation 1. Go ahead and jot that in place. But this is the only equation that we get from equilibrium. We can't sum forces in the x or sum forces in the y, because that's really not applicable. All we're dealing with is this one-dimensional system in torsion, so we can only sum our moments about the x-axis. So we have one equation of equilibrium, but we have 2 unknowns. Here, this is a known quantity, so we just have 2 unknowns, TA and TB. And so that means we have a system that is statically indeterminate. And so that's why we're starting our engineering toolbox. All right, taking this, we move further. What's happening at point C? So at point C, we want to think about the rotations, and we want to think about the rotations along the entire length of the bar. So I want to create what we call our kinematics condition. Remember, kinematics, we relate displacements to one another. And when we're talking about torsions, we're talking about angles of twist. All right, so we know a couple things. We often would say, like, well, the rotation at A is equal to 0. And that's because it's a fixed end. So I think we could write that down as one of our kinematics conditions. We could then keep moving along the length. We would say that the total angle of twist at point C is equal to the twist at A plus the twist of point C relative to point A. And we could take this a step further, and we could look at the angle of twist at B, and B would equal, well, we could just keep adding them along the length. It would be the twist at A plus the twist of C relative to A, plus the twist of B relative to C. And that's an interesting kinematics condition because it kind of provides this relationship. However, in our case, right, this is 0 because it's fixed. And also, we know that point B is fixed. And so if point B is fixed, this angle of twist is also 0. So we'll say both of these are fixed, hence they're 0. So from our kinematics conditions, we can see that the rotation of C relative to A plus the rotation of B relative to C has to equal 0. And so this is our second equation, part of this kinematics condition. Now they're additive because one angle of twist will be counterclockwise, the other angle of twist will be clockwise, and so the plus and minus will offset one another. Finally, we move to material law. So in material law, we want to come up with an expression that relates angle of twist to our torque. And we came up with that expression the last time. We said that the angle of twist for any given segment is equal to TL over GJ for that particular segment. And so this is material law. It relates forces or torques to angle of twist. And this would be our third equation. So, much like we did one-dimensional axial rods, axial deflection, we were able to step through equilibrium, kinematics, and material law to solve statically indeterminate systems. We're able to do the same here. And so we're going to do an example next that'll take us through these steps, but the example will look very much like this setup. And all we'll need to do is take our material law, we plug that back into our kinematics condition, apply the appropriate numbers, the lengths, the g's, the j's, and we should be able to plug this into equation 2, get a relationship between the torque at A and the torque at B. Once we have a second equation that relates TA and TB, we will use equilibrium and get an answer for the torques. And then we can solve for shear stress, angle of twist, and all those fun things. All right, so we'll go ahead and dive into our next example. As a civil engineer, we might encounter torsion in overhang details in buildings. So if we take a look at the picture, I've identified an I-beam that's highlighted there in white and says torsion member. And coming from this larger I-beam, there's a smaller I-beam that comes out of the screen at us and has a distributed load. Whether it's just the self-weight or additional loading from above, it doesn't really matter. That distributed load creates a torque on the torsion member. Now, at this point in our mechanics career, we're not quite ready to tackle torsion of an I section. So right now we've studied what we call St. Venant torsion, but I-beams are subject to both St. Venant torsion and warping torsion, and we won't cover that until a more advanced mechanics and materials class, perhaps in your future engineering curriculum or in a graduate engineering curriculum. So I want to now just focus on what happens if we took that I-beam member and replaced it with a circular member. Now we could totally do this for construction reasons. It's easier to use the I-beam, but just know that in either case we have to design this member for torsion, and because it would be anchored in at both sides, we could consider it as this fixed scenario with a torque applied that we studied when developing the formulas. Alright, so with just exclusively looking at St. Venant torsion, let's draw a torque diagram for the tube and calculate the maximum shear stress. So due to the applied torque at point C, if we had an applied torque of 500 pound-inches that is counterclockwise, using our x-axis, then our supports would have clockwise applied moments drawn in as I indicated there in the figure. So we have two torques, torque A and torque B, that are clockwise to counteract the applied torque. So using equilibrium, we can develop our first relationship. Remember, in equilibrium, we develop relationships between forces. So if we were to sum our moments about the x-axis, we can sum our moments and we'll find that the torque as C is counteracted by the torques A and B. So we have TC minus TA minus TB equals 0, or that TA plus TB has to equal the torque at C, which in this case is 500 pound-inches. All right, this gives us one relationship, but we don't know how much torque is being held by support A and how much has support B. We might initially guess that A is holding more because the torque is closer to point A, but mathematically and mechanically we want to prove that that is the case. So drawing a torque diagram, we have we're going to follow those rules that we have for our torque diagrams. So the torque at A is clockwise applied, so that creates a positive jump in our torque diagram. So we'll go from 0 up to some value. Now this value is just the torque at A. I don't know what this is yet. Then we have the counterclockwise applied torque of 500 pound-inches. So this causes a drop down in our torque diagram of 500 pound-inches. I'll just put I'll get rid of the negative. But remember, we drop down as we're moving from left to right. We drop down 500 pound-inches. This brings us to some new value of torque, and that's going to be negative in this case. And it will be some value, and we could call this value TA minus 500 pound-inches. So that might be useful if we have more torques along the length, and we don't really know where this falls. TA minus 500 would be a very broad way of coming up with this torque in this segment. But otherwise, we do know in this case that this has to be the magnitude of the torque at B. In this case, a negative, because once we get to point B, we're going to jump up a positive TB, and that has to bring us back to 0. All right, so either way you wish to use it, both of those values for the torque on segment CB would work in our equations that we develop. The next tool from our engineering toolbox is Kinematic. So in kinematics, we relate displacements to one another. And when we're talking about torsion, displacements means angle of twist. We saw previously in our notes that we are able to determine the angle of twist at B as the angle of twist at A plus phi of point C relative to point A plus phi of point B relative to point C. But because both A and B are fixed in this case, those angle of twists go to 0. And so therefore, the angle of twist on segment AC has to be equal to the magnitude of the angle of twist on segment BC. Now, we have this written out algebraically here because one will have clockwise rotation and one will have counterclockwise rotation. So to make the signs work, we have phi C relative to A plus phi B relative to C equals 0. But again, they're equal in magnitude, they'll just be opposite in sign. Finally, we have our material law. In material law, we relate our applied forces to our displacements. So that means relating torque to angle of twist. And that formula is phi equals TL over GJ. And so we can apply this to any given segment to get the angle of twist on that segment. All right, these are the three formulas we need to do. We're going to substitute formula 3 into 2, get a relationship between the torque at A and torque at B. Using that new relationship, use equation 1 and solve. So the rest of this is just algebra. We just have to mix and match equations 1, 2, and 3 together to solve. And I want to just reiterate that you could actually take the results from equation, you could plug in 3 into 2 and take the results from 1 and plug it into 2, and you could solve it that way if that's your preferred method. Going from equation 3 to 2, we see that TL over GJ for segment AC has to equal TL over GJ for segment BC. And there's a negative sign in there again just to account for our sign convention. So this is just some relationship. And so we can almost think of like the angle of twist. This is how the torque that's applied at C, how does it decide how much goes to the support at A and how much goes to the support at B? Well, it has to do with the proportion, this proportion right here, this equality. So it's some sort of relationship between the length, the shear modulus, and the polar moment of inertia. And so if I write all of this in terms of TAC, which is really the torque at A, I get that the torque at A is related to the torque at B by LBC GAC JAC divided by LAC, GBC, JBC. And this just comes from the math. So we see that some proportion of the lengths, some proportion of G, and some proportion of J will always determine how much of the applied torque goes to either support. In this case, since it was one uniform rod across the whole span, and it was one uniform material, G and J are the same. So it's only going to be a relationship of the lengths. So taking a look at those lengths, we see that the distance from B to C is 80 inches, and the distance from A to C is 20 inches. So I plug in 80 inches divided by 20 inches. So we see here that the torque at A will be 4 times the torque at B. And that matched our initial engineering intuition when we said that, well, we thought that the torque at A would be larger because the torque was more closely located to the support at A. In fact, it's going to be 4 times as large due to the geometry. All right, this gives us another relationship. So now we have this relationship between the torque at A and the torque at B. We also have the relationship from equation 1. So we have 2 equations, 2 unknowns. We can now solve this problem. And so we come in, we have TA plus TB had to be equal to 500 pound-inches. We substitute equation 4. Equation 4 says that 4 TB plus TB has to equal 500 pound-inches. And so we get 5 TB equals 500 pound-inches, or TB equals 100 pound-inches, and TA equals 4 times that, which is 400 pound-inches. So this establishes how much torque is at point A and how much torque is at point B. That's critical because that will then inform us as to how much torque is in segment AC and how much torque is in segment BC. And so we now can solve for the max shear stress in these segments. So remember, our torsion formula says that tau equals TC over J, or T rho over J. So since rho and J are the same for both segments, then the maximum will occur on segment AC because that's where the torque is the highest. So now we can solve for the shear stress on segment AC. So that is going to be equal to the torque on segment AC, which we said had a magnitude of 400 pound-inches, or the value of TA. The radius is going to be the outside radius. So that's going to be the outside diameter divided by 2. So that's going to be 5.500 inches divided by 2. And then J is going to be pi over 2 times the outer radius to the 4th. So that's 5.5 divided by 2 raised to the 4th, minus the inner radius to the 4th, which is going to be 5 over 2 raised to the 4th. I have the decimal places out to 3 because in structural engineering, when we deal with these tubular shapes, it's standard that the outside diameter is specified to the 3rd decimal point. So I'm just kind of using industry standard language there. Doing our calculations, we get that the max shear stress in segment AC calculates to be 38.63 pounds per square inch, because I have pounds on top and everything else is in inches. All right, so there we have it. We solved for the shear stress in segment AC. I hope you're able to learn something from the statically indeterminate problem, and we are almost done. All right, I think you've earned a good solid milkshake. So go ahead and pull up a straw and dive. Whoa, a straw. Hey, another tube, right? Another tube that has some shear stresses going on. We could probably just twist this and we could probably even fail it maybe. This is a paper straw. Not quite failing. But I did want to point out I've covered one type of statically indeterminate problem, just like we did with one-dimensional axial forces, where we saw we could have a composite system where we have 2 materials that are bonded together and displacing all at once. We can have that for torsion systems too. So imagine just taking like our noodle or our straw and then filling in the inside. So maybe having like a steel outer core and an aluminum or brass inner core or something like that. And then when we apply a torque, the torque would be shared between the materials, but we would know that their angle of twist at one location would be the same. So the torque in the steel plus the torque in the shell plus the torque in the core would have to equal the total torque applied. Set their angle of twist equal to one another, and you can get the relationship between the torques. I really wanted to take you through an example of this, but the more I thought about it, I really struggled to find a real-world application for this, and I called my mechanical engineering friends, and I couldn't really find an example there either. So for now, I think you know enough with the statically indeterminate system we did take a look at, and I think that has earned you a solid milkshake. I've gone for a little bit of a chocolate vanilla twist, and hope you have a good rest of your day.